Sometimes I say that, and yet we're here like the whole time. But this part, in chemistry, we oftentimes prepare solutions. A lot of times we use water as the solvent, and they're called aqueous solutions. And then we use those solutions in our reactions. So, like for instance, the other day, when we used acids, we described how concentrated those acids were with regard to their molarity. So we're going to talk about two ways of describing how concentrated a solution is. So basically, whenever you're talking about solution concentration, you're saying how much solute. Now, there's a lot of S's in solutions, right? We put the solute in the solvent to make a solution. I kind of wrote that on the board the other day. So solution concentration is usually the amount of solute per given amount of solution. But in general chemistry, in the first semester, we talk about another important type of concentration, which is solute per amount of solvent. That's actually molality. So a couple of generic terms. If somebody says it's a dilute solution, that means there's not much solute. If it's a concentrated solution, there's a lot of solute for a given amount of solution. Those were just kind of generic, concentrated solution, dilute solution. You're probably kind of familiar with that. The two things that I want to talk about how concentrated a solution is in terms of solute to solution are these. Okay, so there's grams of solute per liter of solution. Now, this is not very unpacked. So actually, grams per liter means grams of solute, that's the stuff you're dissolving, per 1 liter of solution. Okay, that's what that means. The other one I want to talk about and make sure that you can manipulate this is even more common than grams of solute per liter of solution. It's moles of solute per liter of solution, affectionately called molarity. And actually, when we dealt with those acids last Thursday, the capital M meant molarity. Okay, so if we were going to unpack what that means, molarity means moles of solute per 1 liter of solution. And usually I abbreviate my solution SOL''N. Okay, so that's how concentrated a solution is. Moles of solute that you dissolved in 1 liter of solution. So we're going to do some problems, kind of looking at those. So whether it's moles of solute per liter of solution or grams of solute per liter of solution, anytime you're dealing with volume, like liter of solution, volume of gases really, but liquids to a lesser extent, volume is really dependent upon temperature. One of the things that liquid water will do is if you take liquid water at 25 C, and you figure liquid water will freeze at 0 degrees C. So if you cool that water down, its volume will get smaller and smaller and smaller. Gases are even more crazy. If you take a gas at 25 and cool it down, that volume is going to get less and less and less and maintain the same pressure. So these are dependent upon temperature to a certain extent. So let's do a problem. And usually for these sort of problems, I'm doing it less than I used to, but I like to make a picture. Okay, so if you make a picture of what this says, I don't know if it'll help any, but it basically says what is the concentration in grams per liter, so question mark grams per liter, that's what that means. Okay, if you prepare a sucrose solution, and it gives us the formula for sucrose, and then I can draw an arrow and it says that I am going to dump 32.3 grams of, I'll just abbreviate it, sucrose, SUC. SUCC has that. I'm going to put 32.3 grams of sucrose, and we have the formula up there, in this solvent, right? That's my solute. I'm going to use water as my solvent, so this is what, an aqueous solution. And my total volume of my solution, so I usually kind of go over here, that volume is 225 milliliters. Okay? So here's the diagram of the problem. That's the mass of the solute we're dissolving, and we're going to get 225 milliliters of solution. Okay? So don't make it harder than it is, right? When we work this problem, you know what all we're going to do? We're just going to take that grams, okay? We're going to put it in the numerator. We're going to take that volume, and we're going to put it in the denominator. One thing, quite frankly, we need to fix about the volume is it's in milliliters. So one of the things for this unit that you're going to want to remember is 1 liter is exactly equal to 1,000 milliliters. So we are going to have to go ahead and kind of do that little fix-it step. So this is what it looks like. Solution, no pun intended, right? So we take that mass of the solute, divide it by the volume of the solution. Okay, so far so good. If we were to stop, you know, we're all about working these problems, focusing on the units. If we were to stop right now, we'd have units of grams of solute per milliliter of solution. So we can't quite stop. So we need to fix the denominator. So if we want units of milliliters to cancel, do you see where we're going to put 1,000 milliliters over 1 liter is our next term. And then we're done. Okay? That term, that second term there, is just to kind of fix the units of milliliter into units of liters. So like I said, we're all about following not the money, but the units. So grams of, and if I'm only dealing with one, we call these one analyte, one species, a lot of times I won't put C12H22O11, okay, as long as it's just one thing I'm worrying about. Sometimes I'll label this and say, oops, sorry, that doesn't cancel. Okay, so thank goodness that doesn't cancel. So what does cancel between these two, of course, is units of milliliters cancel. And we're left with units of grams of C12H22O11, or grams of SUCC per liter of solution, and that's it. Then round it to 3 significant figures, right? Okay. So you would get 144 if you round to 3 sig figs. Now we could say it's 144 grams per liter, or 144 grams of sucrose, C12H22O11 per 1 liter of solution. Okay, that's kind of the explicit way. Usually if you're writing a report or something like that, you'll write it kind of linearly G/L. But remember what G/L means. Okay, it means grams of solute, in this case sucrose, per 1 liter of solution. So, all right. So I said there's two ways I want you to describe how concentrated a solution is. This is how concentrated the sugar solution is in grams of sucrose per 1 liter of solution. The other one is molarity. Okay? So actually the example I'm going to do is to take that same situation, that same solution, and now instead of 144 grams of sucrose per liter of solution, I want to get moles of sucrose per liter of solution. And this is what I want to do here is basically piggyback on the answer we already have. So if you figure we have 144 grams per 1 liter of solution, to get from grams to moles, we need to knock out the molar mass of sucrose and insert it basically as another term. Okay, so the molar mass of sucrose, of course, you need the decimal number for carbon times 12. 12 times 12.01. Plus the decimal number for hydrogen times 22, so 22 times 1.008. Plus the decimal number for oxygen, 16.00 times 11. So, you know, sometimes I'm better about it than others, but remember, whenever you guys come up with, this is an MM, right? That's the molar mass of C12H22O11. Whenever you come up with the molar mass, remember that means it is 342.30 grams per 1 mole of that compound. Okay? All right. So like I said, if you're okay with this, I just want to piggyback on what we came up with in the first problem. As far as grams per liter, we have 144 grams of sucrose per 1 liter of solution. Now I'm going to insert molar mass. I want grams to cancel with the first term, so I better put units of grams in the bottom for my second term. So it's going to be what? The flipped version of the molar mass. So it's going to be 1 mole sucrose, S-U-C-C if you want, 1 mole sucrose per 342.30 grams SUCC. So that's the molar mass, right? And doing it this way, now our grams will cancel, and we'll be left with units of moles per liter. And that's what molarity is. That was our goal, moles per liter. Looks like we're stuck with 3 sig figs. I got 0.419 rounded to 3 sig figs. 0.419 moles sucrose, SUCC, per 1 liter of solution. I mentioned the big M. So what you'll usually see it written as is 0.419 big M, capital M. I emphasize capital M because for whatever reason they stuck with a lowercase m for another important type of solution concentration called, and it's really similar to molarity, it's called molality. So welcome to the world of chemistry. You're like, dude, could you not have come up with something more, you know. So molarity, capital M. Moles of solute, in this case sucrose, per 1 liter of solution. And you're done. So the best way to get these under your belt, is like a lot of things in chemistry, is to kind of do problems yourselves. So that's why here in a minute I'm going to show you what's due for Wednesday. If somebody said, what's the molarity of this solution? Okay, they would have to know what the green stuff was, knock out the molar mass of the green stuff. I would probably take that mass you saw on the scales divided by the volume of this volumetric flask. Okay, my next term would be the molar mass. Okay, as long as this is in liters, you wouldn't have to even convert from milliliters to liters. Okay. So, and if you use the factor label method, and you should be fine. So this is actually just kind of a figure from your textbook that shows the same thing. Kind of you take your solid solute, okay, you put it in your volumetric flask that has the cool skinny neck, okay. Usually you put water in there and kind of squish it around. Some things dissolve faster than others. Some things you got to leave them overnight, right? But you usually dissolve it before you bring it up to volume because it's a lot easier than there's room to swish it around, quite frankly. It's a practical sort of thing. Once it's dissolved, basically, okay, then you top it off with water. That last step is very important. Did you see, I don't think they showed you, but the whole mixing, once you bring it up to volume, is very important because I've not done that sometimes. And so what happens if you don't mix it with your last dilution in a volumetric flask, you have like weak stuff up here and concentrated stuff down here. So that's how that works. All right, so let's take a look at these. These have a few parts, but I'm going to push these hints out there. Notice the instructions for the test, the instructions for your homework are the same. You got to show kind of that molar mass calculation on the front end, okay, to get full credit. So let's see. Where did you go? This should be you. So you'll see there's a part A, B, and C to this one. I kind of basically did A for you, if that's okay. Okay, so it says calculate the molarity of these solutions. So in each of these cases, A, B, and C, they give you the moles and they give you the volume. And like I said, I'm going to push this out on my Twitter feed too. So for A, you're going to divide the moles, which is 0.127, by the volume, which is 655 milliliters. Okay, and you'd be done if you didn't have to fix the milliliters into liters. So we do need to introduce that second term to make milliliters cancel, be left with moles per liter. Okay, so that's it. And actually the other two are the same. So you don't have to calculate a molar mass for this problem.
Mrs. Ramsey, will you have like our test thing, you know, that you hand out before the test? Do you think you'll have that by Friday so we can get it up for the weekend?
Oh.
Since our test is next Thursday.
Thanks for reminding me. Yeah, yeah, kind of like an outline of what you guys are. Yes, I will. I might not if you hadn't asked, so very good. So the next problem looks like this. Okay. These are similar, 61 and 63. Now you're supposed to calculate the molarity. It's kind of like we did the sucrose solution. You're supposed to calculate the molarity, but all they give you are grams and volume. So in this case, you're going to have to, molarity is moles per liter. So you can't just divide grams, can't stop. You start there. Divide grams by volume, that's fine. But then you need to go ahead and get from grams to moles. And to do that, we need the molar mass of the thing that you're working with. So I went ahead and kind of outlined A for you. A gives you 22.6 grams of C12H22O11, and it gives you a volume of 0.442 liters. So what I would do, I kind of showed you down here at the bottom here. This is A, okay? For 61A, what I would do is go ahead and divide that grams by that volume. And then in purple out here, before I work the problem, what I have is calculate the molar mass of C12H22O11. 12 times the decimal number for carbon, plus 22 times the decimal number for hydrogen, plus 11 times the decimal number for oxygen. That's what we just did, isn't it? So you're going to, this actually, the second term here is the molar mass. Notice I'm using the flipped version of the molar mass. If I do that, then my grams will cancel, and I'll be left with moles per liter. That's it. Okay? So I've already kind of outlined 61A for you. 61B, different compound, different molar mass. So I would take that grams divided by those liters. My next term would be the molar masses of NaCl, the flipped version. Let's see. Let's look at C. For C, you're going to need to remember, and I bet you will. Oops, that's not. What's that? Yes, for C, you need to remember that 1,000 milliliters is equal to 1 liter. And also for C, you need to remember about the milligrams too. I bet you're okay with that because it's very similar. Okay, so yeah, for this one, like you said, 1,000 milliliters equals 1 liter. And then how about, and that's an exact relationship, how about milligrams? What do you think? How many milligrams is equal to 1 gram? Yes, exactly. So it will look a little different. It'll have another term in there to correct from milligrams to grams. Okay? So as long as...
Do you want us to go ahead and switch that to milligrams or switch it to grams before we do the problem, or do you want us to put that step in our problem?
Probably the latter, I think, is cleaner, but you don't have to. You can do it outside of the problem and then string them up, so that's fine. Because what it would look like here would be what 315 milligrams over the volume, which was 58.2 milliliters. Okay, and if you're going,
you would do your 1,000.
I would.
Milliliters.
I would. 1,000 milliliters over 1 liter. I like that. And then what about fixing the milligrams to grams? I know. It'd be 1,000. Since milligrams is in the top, I have to put milligrams in the bottom. That's kind of how I would start that one.
But nothing cancels, does it?
Well, so let's see. Let's see, milligrams here cancel with milligrams here.
Oh, okay.
Yep. And milliliters.
There we cancel with milliliters.
Yeah.
And then you'd be left with grams.
And I'd be left with grams.
Grams per liter.
Yeah. So then I'm ready for the molar mass. So I'll just go ahead and put the, and then you'd be done, actually. I'm going to put MM here, molar mass of C6H12O6.
And the molar
Molar mass
would
goes
be
here.
grams per mole.
Yeah. Mm-hmm.
But wouldn't it be the flip version? Because
Right.
when you need the grams.
Yeah,
on
yeah,
the
I didn't mean
okay.
you, I didn't.
Okay, I was just making.
Yes, it would be the flipped version. Very good, perfect. I'm liking it. So let's see, let's look at 36 and, 63, and it's very similar to 61 because it gives you the mass of NaCl and it gives you the volume of the solution. All right? Okay. On to one other type of problem with solution concentration. So do you remember way back when, beginning of the semester, we said that if you have like a physical property of something, like if you have the density of something, okay, density is grams of liquid usually, or it could be solid, per milliliter, for instance. So give the volume, grams per milliliter. If you have the density of something, you can actually use it as a conversion factor to go back and forth between grams and milliliters, okay? So we can use these two things, these two ways of expressing how concentrated a solution is, to go back and forth between what the units are. So if the concentration is units of grams of solute per liter of solution, we can go back and forth between grams and volume, okay, mass and volume. If we're talking molarity, okay, if that's the way the concentration is expressed, moles per liter, we can go back and forth between moles and liter, okay? Use molarity as the conversion factor to go back and forth between moles. And we won't get to this today, but actually, this is another type of problem. Do you remember the egg, right? Okay. When you guys came up with, for instance, your shell, you said your shell was, I don't know, 12% by weight. So it's 12 grams of shell per 100 grams of egg mixture. Actually, we can use that as a conversion factor too. All right, so let's do the first two though. Let's say the analyte or the solute, I guess I should say solute is a better way to say it. So what was dissolved in water this time was sodium chloride. They went ahead and told you how concentrated it is in terms of grams per liter. So actually on the next slide, you're going to see me, I use the word unpack. Okay, that's the concentration of the sodium chloride solution. So really what that means is 14.3 grams of NaCl per 1 liter of solution. That's what that means. Okay, so if we read it a few times, you know, if we're going to diagram it, it says what volume. So I could put like volume over here, right? What volume, question mark volume, of solution will contain 22.3 grams of NaCl. So we're going from 22.3 grams of NaCl to a certain volume. So can you see where my first term is going to be 22.3 grams? My next term, quite frankly, not to give it away, okay, but do you see where if I introduce the concentration of sodium chloride, I can do what the flipped version of that. And my grams will cancel and I'll be left with volume per liter of solution. That's it. That's kind of all we're doing here. Okay, so the concentration was given. It's like a physical property of that particular solution. Not to say it couldn't be more concentrated or less concentrated, but that's this solution, 14.3 grams of NaCl per 1 liter of solution. I kind of told you it looks like we're going to use the flipped version of that in our problem. You know, that's also a physical property. In 1 liter of solution, it would contain 14.3 grams of NaCl. We could also kind of think of it as kind of for this solution, 1 liter solution is equal to 14.3 grams of NaCl. So diagramming it, like I said a minute ago, it kind of looks like this. We're given that grams and we're trying to get to volume, specifically liter of solution. And to get there for this solution, we can use kind of the equality, 1 liter solution is equal to 14.3 grams of NaCl. So the first term is going to be the thing we want to convert. Okay, 22.3 grams over 1, 22.3 grams NaCl over 1. So if I have grams in the numerator and I want grams to cancel, be left with liters, can you see why this is what the second term is? It's the flipped version of the concentration. So units of grams of NaCl cancel, and we're left with liters of solution. As far as I can tell, we're done. So we round according to 3 significant figures. So the volume of solution you'd need at that concentration to know that you had that mass of NaCl is 1.56 liters of solution. And that's it. See, they're kind of a little bit straightforward, but once you guys do your homework, I think you'll do fine on the test. And if you just look at your units, it kind of works out okay. So, remember I said if you only have like one solute or one species, one analyte, you don't really have to explicitly say NaCl or the sucrose or whatever. But this says be careful because sometimes, especially when we work that weight percent problem, probably on Friday, you'll have grams of 2 different things and they do not cancel each other out. Especially with weight percent problems. And density problems actually too. Okay. So let's do another problem. Instead of sucrose, instead of NaCl, the solute this time is potassium dichromate, K2CR2O7. And it looks like they give us the molarity, 0.255 molarity. And actually on the next slide, you're going to see us unpack this again. You know, what does this mean? Anytime you see an M, I should never see you work problems, set them up to show your work without unpacking what that M means. What that M means is, in this case, 0.255 moles of K2CR2O7 per 1 liter of solution. That's what that means. So if we were going to diagram this, kind of lift out from the words, if an experiment calls for 0.015 moles, how many milliliters? How many milliliters? So I think I'll put question mark milliliters over here. Question mark milliliters. How many milliliters? Okay. And actually, my first term is going to be my target moles, 0.015 moles. Do you see where we can use this to get from moles to liters? Okay. If we just, and see, we'll have to again use the flipped version, won't we? You see, if we flip that as our second term here in a minute, our moles will cancel. We'll be left with liters. And then we need to do one more thing to get from liters to milliliters. So this is going to go there. And of course, to get from liters to milliliters, you guys told me I can use 1,000 milliliters. It's equal to 1 liter. So in this case, we're going from liters to milliliters, so milliliters to liters. So that's kind of what we're going to do. So here's the unpacking of that molarity. Okay, so what 0.255 M, capital M, means, you can't use it just like that. It means moles of solute per liter of solution. The flipped version is cool too, and actually we're going to have to use the flipped version because we want moles to cancel. We won't always use the flipped version, but and we could kind of flatten it out for this given solution. All right, work this problem. So the strategy, like I said, is we're going to go from moles of K2CR2O7 that were given to liter of solution using the molarity. And then we're going to go from liter of solution to milliliters of solution using that with the metric system thing. 1,000 milliliters is exactly equal to 1 liter. So the first term is moles over 1. 0.015 moles. 0.015 moles K2CR2O7 over 1. And then we want moles to cancel, so our next term is going to be 1 liter of solution over 0.255 moles of K2CR2O7. Moles will cancel. And this particular problem wanted the volume not in liters but in milliliters. So since we want liters to cancel, we're going to have to put liters in the bottom, and it looks like we'll put 1,000 milliliters on top. So our third term will be 1,000 milliliters over 1 liter. So this actually is kind of a continuation there. So if we look for what cancels kind of from left to right, our moles have canceled, our liters of solution have canceled, and we're left with units of milliliters of solution, which is exactly what we want. So it looks like, I bet you by this, hopefully, that with regard to sig figs, I can only have 2. I can only have 2 significant figures because I have 2 there. Of course, there's uncertainty brought by the molarity, and I have 3 significant figures there, and there's no uncertainty brought by things in the metric system like that. So rounding it to 2 sig figs, your volume is 59 milliliters. 59 milliliters of solution. So if you bought into kind of the using the factor label method and making your units cancel early on, these kind of are that should work in your favor. All right, another problem. How many moles of something else now? We know that is calcium chloride. How many moles of calcium chloride are there in that volume given that molarity? Can't remember if on the next slide I do this, but one of the things that you're going to want to do is recognize what the big M means. 0.108 moles of CaCl2 per 1 liter of solution. And honestly, if you unpack it like that, then it looks available to you to use in your problem. And then if you kind of start diagramming kind of what you're after, it says how many moles, so that's what I'm trying to end up with. How many moles of calcium chloride, okay, are there in, honestly, this is what I'm going to start with, 75.0 milliliters. Okay, so maybe you see this, but if this were liters, notice if this were liters instead of milliliters, then I could go ahead and use this to get from liters to moles, okay? But it's not liters, so I just need to make it liters first, okay? And of course that's from 1,000 milliliters is equal to 1 liter. And then once I get it to liters, notice I can go ahead and go all the way to moles using this. Once I have it in liters, I can go ahead and my liters will cancel and I'll be left with moles, so I don't have to flip it then, right? All right. So this is kind of how that looks. Milliliters to liters, using 1,000 milliliters is equal to 1 liter, and liters to moles using the molarity. So the first term is our milliliters over 1. Milliliters over 1. Then we want milliliters to cancel, so we'll put what? 1 liter over 1,000 milliliters is our second term. And milliliters will have canceled, and we'll be left with liters. And then we go ahead and bring in the molarity. And since we want liters to cancel, we're going to use the non-flipped version of the molarity. 0.108 moles of calcium chloride per 1 liter of solution. So if we just kind of take one last look at what we thought we had canceling, Notice milliliters of solution have canceled. Liter of solution have canceled. And we do have units of moles, which is cool. And sig fig, or rounding wise, notice we have 3 significant figures here. And over here we also have 3 significant figures. The 1 and the 8 are significant because they're not 0, and that 0 is significant because it's between 2 non-zero digits. So it looks like we round according to 3 significant figures. So rounding according to 3 significant figures, notice when your calculator displays it that those first 2 digits, okay, the 0.00, those are not significant. So to get 3 sig figs, and I'm not sure, I don't have my calculator handy to see what I rounded to or left alone, but you need to show a trailing 0 after the decimal to get 3 sig figs. All right. Now do we have an assignment slide?
This is our last problem.
Okay. I was like, aren't these ending? Thank you. I'm getting antsy. Okay, another problem. Different solute. Okay. This is a good one. Let me think. No. I am debating. Let me see my brain going. Let's see. Part 3B. So this is the assignment slide we're bumping up against.
Are we doing all of them?
Well, that's what I'm debating. Okay, let's do it this way. I'm going to hold that one example problem. Okay, so what I want to be due on Friday are just these 2 problems, in addition to the others that we talked about.
We have 4 due Friday.
Yes, 4 due Friday. So let's take a look at my hints here. So we'll have one more example problem before the assignment slide. And then I'll assign the other 2, or the other 3, I think. But anyway, 65 and 67 are also due on Friday. So if we look at these, this is what we've been talking about so far. So 65, I did 65A for you. It says how many moles of NaCl are there in each of these examples? And for each of them, they give you a molarity and a volume, a molarity and a volume, a molarity and a volume, and they want to know moles. Okay? So basically, if we put the volume as the first term, okay, we use the molarity, and then we can get to moles. So I went ahead and did A for you. Okay, so we're going to use that 1.5 liters. The molarity is 1.2 molar. That's 1.2 moles per 1 liter. Liters cancel, and you'll have the answer. You don't need to calculate the molar mass for these.
So the one that's in milliliters, though, we're going to have to
Right, the ones, yeah, for, looks like
see.
for C. Yep, you're going to have an extra term for C. Yep, you got it. And so for 67, it's what volume, so I put question mark volume over here. For 67A, I did what volume contains 0.15 moles, okay? And actually, in this case, they want, the first term is always going to be 0.15 moles. It's just they're going to change the molarity. So for the molarity for the first one, it's 0.255 moles of potassium chloride per 1 liter of solution. So my hint for that one, again, we're going to start with the 0.15 moles over 1. Then notice here in blue, we're going to use the flipped version of the molarity. Yep. To get to, because now your moles will cancel, you'll be left with liters. Any questions? Cool. Das ist das.